So in the electrostatics unit, we're going to be concerned with the same big ideas we've been concerned with throughout physics. What forces do objects experience? And how is work done against those forces as objects are moved to different locations? In general, we have a concept called field, which is related to force. In every force equation, which I've drawn in purple here, part of it depends on where you are and part of it depends on the specific object. And field is the part, either gravitational or electric, that depends on where you are. The same is true with something called potential and potential energy. I've drawn basically the equations for potential energy, and everything to do with location is in red and everything to do with the object is in green. So potential is the location specific part of potential energy. It's one thing to say that. I think it's important to understand how charges affect the space around them. And I think having some hands-on experience with this is really important. So we're going to do a lab produced by the University of Colorado as part of their PhET simulations. And what you're going to do, you're going to visit this link, you're going to open up the sim, and it lets you put various charges into space. And it lets you measure electric fields caused by them. It lets you look at directions of forces. It lets you measure potentials in different locations. And what you guys are going to do is just kind of see what these do to space. So I did this as a demo in class, this one. We saw that if we just put a positive charge in space, any little tiny test charge I brought there is going to experience an outward force. So we draw the electric field lines like this because a positive charge would be repelled by it. Now, of course, a negative charge would be attracted by it. And we have to sort of remember that when we draw electric field lines, electric fields affect both positive and negative charges. Negatives move against the field. Excuse me, negatives experience a force against the field. So we still draw it as if it's a positive charge. And we just have to remember that if we bring a negative here, the force is in the opposite direction. I then asked the class if I had a charge and I put it, say, here. I asked them where they would expect other charges to have the same potential energy. And they told me in a ring around the first charge, that if I put this guy anywhere here, it would have the same potential energy. Similar to that. So the equipotential lines around a positive charge, the places where some object would have the same potential energy, are spherical. So that's the part that depends on location. We say that everything on this sphere has the same potential. So visualizing this in multiple dimensions, I think, can be a challenge. And I want to show you a technique that can be helpful for understanding the potential as you move away from a positive test charge. So here's a better picture of what I just did. Any positive charge, like this cursor, is going to experience a force away. And it's going to be moving to lower and lower potential energies as it moves to these different potentials. If we sort of graph electric potential on a z-axis in a 3D chart, it becomes easier to see what's happening. This positive charge would be going to lower potential energy, and it would be being converted into kinetic energy as it rolled down this mountain that's electric potential is represented by. So we would expect a force downward if this was a ball. We'd expect going to lower potential energies and therefore higher kinetic energies. So we can imagine this charge kind of rolling down the mountain. Of course, we're at a negative charge. It would be being sucked up the mountain. That's kind of a hard thing to see. That's difficult about static electricity. It can be both attractive and repulsive. So hopefully this helps you understand Certain locations contribute differently to potential energy, and forces are what cause objects to move from one area of potential energy to another. So in what direction would a negative particle experience a force in this case? Well, a negative particle experience a force against the field lines. So we would say inward. A positive particle experience a force with the field lines. So we'd say outward. Bringing a positive particle to potentials that are closer and closer to the positive, that would require the most work. And a negative particle, it would have the lowest potential energy when it's closest to the positive, so it would require more work to bring it away. So what I asked students to do now was finish this lab for a number of other situations and just try to see what's happening with both field and potential as we go near various types of charges. So if you weren't here, that's something I'm going to ask you to do. But let's just take a quick look at what you'll see. I had students look at a negative charge. Notice that the field lines point inwards because a positive would be attracted to that negative. And obviously there's also spherical potentials around it. So in 3 dimensions, it would look like this. A positive would fall to lower potential energy. It would speed up as it did that. It would gain kinetic energy. Here's the equipotential lines in yellow and the electric field in red if you have 2 positive charges. Notice the electric field lines approach each other but don't cross. That's because the electric field shows you the direction of the net electrostatic force in a location, and you can't have 2 net forces. So right here, we would see this positive charge is being accelerated that way. Here it's being accelerated that way. We have sort of strange looking potential lines. They kind of bunch up in the middle. And what's happening there, if we plot it in 3D, is we sort of have a saddle shape. This would fall to lower potential energies, but if it stayed directly between them and continued this way, it would then go about higher potential energies. So with a saddle, it could fall off here and go behind, or it could fall off here and go up front. But basically, there's no place where the contribution to potential energy from one is completely canceled out by the other here. Because if we're going in this direction, here we're falling to lower and lower potential energies, but now we're going back to higher and higher. And the shape of the saddle really shows that. Contrary-wise, if we have a positive and a negative, in some ways, the equipotential lines look kind of similar. Notice that the field lines look pretty different. In this case, we'd always experience a force away from the positive and towards the negative. But in this case, there really is a place where the potential from one object and the potential from the other object, there is a halfway point between them, where we're at a potential halfway between them. So that's a little bit different. What we would do in class, if we were doing a real lab on this, we wouldn't just use the PhET lab. We would actually cause different potentials in a field. This is conductive paper. And I don't know if you can see this, but there's little dabs of black paint there. And we can actually cause one of these pins to have a positive potential and one of these pins to have a zero potential by hooking it up to a power supply. And what we would do is we treat this as a positive charge, this is a negative charge. And we'd go around and we'd plot the various potentials and we would find equipotential lines. And we would see similar patterns to what you guys just saw. I asked one other situation. I asked people to look at a line of charge. So I had people put lots of positive charges in a line and lots of negative charges in a line. And sort of what we see in between is we see that between them, we have a really constant electric field. No matter where you are here, if I've got a positive charge, I'm always going to be repelled from the top and attracted to the bottom, and vice versa for a negative. So if we were going to do a 3D picture of that, it would actually be something like this. Positive charges would be like rolling down a ramp. Negative charges would be like rolling up a ramp. Parallel plates like this are a device called a capacitor. We'll spend a fair amount of time talking about them in class because they're not only useful for causing constant electric fields like this, but they're a way of storing energy. But the best way to understand the energy of a positive charge as you move it around inside a capacitor or a negative charge is to think about how a constant electric field like this is very much like a constant gravitational field like we would have in our classroom. We know that if the gravitational field is constant, the potential energy at any height above the ground is mgh. Whether it's a big mass or a little mass, the GH part of mgh just depends on where you are. So we could say this is one gravitational potential, another gravitational potential, another gravitational potential. And they have the equation GH to describe the potential. The potential energy of an object in that case, mgh, you just multiply the mass times the gravitational potential. So we could do that with charges as well. We would have one electric potential at the negative plate. We'd have another one in the middle, another one here. And it would be an increasing electric potential as we see here. And what's the potential energy of a charge in any case? QED, which is just the electric version of mgh. What's the potential in any place? Just ED, the GH for electricity. And we can calculate a potential energy at any location by multiplying potential by charge. So we can check this in the lab if we paint stripes on the conductive paper. And we can verify this with our voltmeter that it will read 0 at the negative plate and it will increase somewhat linearly as we move up, and it will read 6 at the top plate. I hope that helps a little bit with your understanding of potential and field. These are challenging concepts, and having some hands-on experience I think is important. Hopefully doing the PhET labs gives you that hands-on experience.